Hi, this is Lavanya Sitaraman. I'm presenting paper on making smartphones smart on demand with the radio interface management. A major concern for today's smartphones is a faster battery drain than the traditional feature phone despite their greater battery capacities. Because of more power consuming smartphone components such as multi-core application processor and high definition displays are used in the smartphone. If you are trying to increase the battery life of the smartphone by minimizing the use of the application processor and the HD display for the operation related to the basic function. Authors found that the application processor is often waken up by the process running on it called Radio Interface Layer Daemon (RILD), which interface the users and the apps to the cellular network. As I mentioned in the previous slide, while the application processor must be active when any smart apps are being used, it is unnecessarily waken up even during the ideal periods to perform the operation related to the basic functions, that is incoming call and text messages. In addition, the power-hungry HD display is also used unnecessarily for such basic functions. Modern smartphones commonly have the basic baseband processor and the application processor. The baseband runs on the real-time OS that interfaces with the cellular network, for example GSM services. The application processor handles the user inputs from the display and runs all the apps tasks on the smartphone operating system. RILD mainly consists of three components distributed in the various layers of the smartphone: RIL Java, RIL Daemon, and vendor RIL. RILJ and vendor RIL are the entry points of the communication between the apps and the baseband. RILD is the core of the RIL and is a position in the middle to coordinate the solid and unsolid communication. In terms of related work, recent research has proposed a varieties of power optimization strategy for different smartphone components, proposed data batching, and analyze the energy bugs. Some research studies focus on exploiting the application processor, DVFS levels, and heterogeneous configuration to find the best trade-off between energy consumption and the performance. To the best of the author's knowledge, this is the first work that identifies the energy impacts of the RILD on the application processor during the ideal periods and designs a new configuration to systematically improve the smartphone battery life. This figure shows the high-level architecture of SOD, which adds a low-power microcontroller and the secondary low-power display to standard smartphone hardware. When the energy-saving mode is turned on by the user, SOD shifts the duties of RILD from the application processor to the low-power microcontroller, which then handles the communication directly with both the baseband and the application processor, and controls the low-power display through the user interface for the new voice call or the SMS notification. As a result, a separate user baseband path is established so that the application processor and the HD display can be bypassed for this basic phone function and dynamically wake up only for smart apps, that is Skype, Facebook, email chat, in an on-demand manner. And this diagram shows the steps of handling an incoming voice call with SOD and without SOD. There are three possible SOD configurations that can be adapted: controller plus application processor, that is described in the previous slide, and only controller, that uses a slightly more powerful microcontroller to run both operations without need to resume the RILD on the power-hungry application processor. Application processor only, a baseline that executes all the RILD operation on the most powerful application processor. Here, they described the energy model during the ideal periods of controller plus application processor and only controller and application processor only. An ideal period is a continuous period of time spent by the smartphone with the display off without user interaction. We define n switch as the number of times controller plus application processor resumes RILD on the application processor during a generic ideal period. Note that similarly to only controller, only application processor executes all RILD operations on one processor. Thus, their energy model is similar. Therefore, in the following model, we can define E single as the energy consumption of only controller or only APA only, and E mixed as the energy consumption of controller plus AP, where P is the average power consumption and T is the time length of the period. Thus, the multiplication PT is the total energy consumed during T. P idle and T idle is the total energy consumed by controller only or AP only. P rest and T rest is the total energy consumed by controller plus AP. while RILD is resumed on the application processor. T suspend is the total energy consumed by controller plus AP, while RILD is suspended on the application processor. P switch and T switch is the total energy consumed by controller plus AP. Each of the N switch times RILD is being suspended and resumed on the application processor. To run these experiments, they used monsoon power monitor to measure the power consumption of the various smartphones, including LG V10 and LG Nexus 5. Both devices have the dose mode activated during the test. In the dose mode, which is activated at the beginning of every idle period on any Android devices, the system attempts to conserve the battery by restricting the app's access to the network and the CPU intensive services. It also prevents apps from accessing the network and defers their jobs, synchronization, and standard alarms. To evaluate the SOD configuration, all the presented power energy values are directly measured with the monsoon power monitor. They used the measurements to evaluate the total energy savings of SOD with 3 usage patterns: typical, SMS intensive, and voice intensive. A SMS intensive pattern with 300 SMS per day and a voice intensive pattern with 250 minutes of calling time a day. Second, various real user traces collected between 2011 and 2014. When the smartphone is not actively used for smart apps or basic phone function, it is assumed to be idle, that is display off, with an active data connection of either 3G, 4G or Wi-Fi, that is 30% and 70% of the time respectively. SOD is orthogonal to existing research on the smartphone power optimization. To the author's best knowledge, there is no published work that improves the battery life by managing RILD to the knob to degrade the smartphone into feature phone. Thus, authors compared two representative baselines that are the variants of AP only strategy that discussed in the previous slide. That is APH, that is application processor with homogeneous cores. RILD runs on one core of an application processor with two or homogeneous cores. Example Nexus 5. APH with monochrome colors similar to APH but uses the black and white colors for basic phone function. APL application processor with big little cores, that is RILD runs on low power core of an application processor with heterogeneous cores, that is example big little on the LG V10 configuration. APL with monochrome colors similar to APL but uses the black and white colors for the basic phone function. Similarly, they indicate with SODL and SODH the SOD implementation of LG V10 and Nexus 5 respectively. These baselines represent commonly used phone configuration that can be compared with SOD for the energy saving. Here they tested how SOD affects the power consumption and the battery life of the smartphones during the ideal periods. First, they studied the application processor time spent in the active state to study how often RILD threads wake up the application processor. Then they analyzed the energy savings and the battery life gain of SOD during the ideal periods. This figure shows two examples of time frames of the application processor activity. The first graph shows the frame of time between the two consecutive data updates. For APL and APH, the RILD threads, including RIL receiver, that is the RIL thread in the Java side of the Android, frequently wake up the application processor from the deep sleep state. SODL and SODH instead handle the basic phone operations on the microcontroller so that the application processor can sleep more often for the energy saving. Here, with the SOD, even other threads used indirectly by RILD, that is binder, contribute to energy savings because they are not executed while RILD is suspended. In other cases, the application processor of SODL and SODH must wake up to execute other operating system threads, for example, thread hot plug, or to perform periodic data updates, that is shown in the Second graph. Here the test shows how SOD affects the power consumption and the battery life of the smartphone during the ideal periods. First, they studied the application processor time spent in the active state to study how often RILD threads wake up the application processor. Then they analyzed the energy savings and the battery life gains of the SOD during the ideal periods. Here, this diagram shows two examples of time frames of the application processor activity. The first graph shows the frame of time between the two consecutive data updates for APL and APH. The RILD threads, including RILD, the RIL receiver, frequently wake up the application processor from the deep sleep state. SODL and SODH instead handle the basic phone operations on the microcontroller so that the application processor can sleep more often for the energy savings. Note that with SOD, even other threads used indirectly by RILD contribute to energy savings because they are not executed while RILD is suspended. In other cases, the application processor of SODL and SODH must wake up to execute the other threads. If you see the second graph, when the apps are allowed to perform the data updates, RILD forwards the data updates to the apps, that is new email. At the end of the data update period, however, RILD is suspended by SOD again for energy saving. As a result, the total amount of energy savings achieved by SOD strictly depends on how often the application processor is woken up to execute the basic phone operation of RILD. Critic is from my point of view, the paper is lengthy, and if one doesn't know the basic operation of mobile communication, then it will be difficult to understand the paper from the beginning. Thank you.